Okay, Samuel, so we're stuck. Our model's classifying everything as non-nodule, but the overall accuracy looks great. What gives?
Yeah, that's a classic problem with skewed datasets. Our negative samples are overwhelming the model. It's learning to predict non-nodule, because that's the majority class.
So, accuracy isn't the whole story here?
Exactly. We need to look at something else, like precision and recall.
Precision and recall? Tell me more.
Precision tells us, of all the things the model predicted as nodules, how many were actually nodules. Recall tells us, of all the actual nodules in the dataset, how many did the model correctly identify.
So, if most things are non-nodules, the model could be super accurate but completely useless?
Absolutely. We need to focus on correctly identifying the nodules.
This chapter's about improving that, right?
Exactly. We're talking about evaluating our model's performance beyond simple accuracy. This step is crucial for developing a truly useful model.
Makes sense. So, how do we get a model to correctly identify nodules instead of ignoring them?
Well, we can try different evaluation metrics, and also we can change how we've trained the model. We might want to rebalance our dataset.
Rebalance the dataset?
Yeah, try to have more samples of positive cases. We can even introduce techniques like oversampling, creating synthetic copies of rare classes, or undersampling, reducing samples from common classes.
Okay, that's one path. Any other approaches?
Absolutely. We could also use cost functions that penalize misclassifying important classes, or we can tweak the model's architecture to give more weight to the positive cases.
Okay, Samuel. So this chapter outlines a plan for improving our model. Figure 12.2 is this abstract map, right?
Yeah, it's a high-level view. We're tackling issues like over-reliance on single metrics.
So, these single metrics are problematic?
Exactly. They don't give a complete picture of the model's performance.
Makes sense. And these guard dogs and birds and burglars metaphors? What are they for?
They're meant to make abstract ideas more relatable. Like, picturing these things helps understand the issues better.
Interesting. So, then we're moving on to something more concrete?
We're developing a language to explain the problems better, like with recall and precision.
Ah, recall and precision. Crucial concepts in machine learning. Tell me more.
It's about how well the model finds what it's looking for. Recall is how much it catches, and precision is how accurately it identifies them.
So, we'll see how these metrics improve our model?
Absolutely. Then we'll have a new metric, the F1 score.
F1 score, a single number to summarize.
Yup, summarizing the recall and precision. A single number summarizing the model's overall performance.
This is crucial. And these Luna dataset changes?
Balancing and augmentation techniques to make the training data more representative. That's to improve performance further.
So, after all this, the model will be better?
Yes, good enough to handle the nodule candidate classification, but not ready for clinical use yet. Then we can consider segmentation and grouping.
So, a step-by-step improvement. This makes a lot of sense. Are there potential pitfalls in all this?
You know, sometimes balancing data too much can introduce bias. Augmentation can also be tricky. It's all about finding the right balance.
Great insights, Samuel. Thanks. So, these guard dogs, Roxy and Preston, they're a pretty good analogy for machine learning models, huh?
Yeah, absolutely. Roxy's like a model that's overly sensitive. It flags everything as a potential burglar.
So, false positives. Can you explain that?
A false positive is when a model identifies something as important, when it's not. Like Roxy barking at a squirrel.
And Preston?
Preston, the sleepy hound, is a model that misses important things. False negatives.
False negatives, that's tricky.
He's like a model that doesn't spot important things, like a cancer in a medical image.
So, how do we balance these?
It's a tricky trade-off. You want to avoid both false positives and false negatives, right?
How do we do that in the real world?
You gotta tune the model settings. Adjust the thresholds. Find the balance.
That sounds complicated.
It is. There's no one-size-fits-all solution. It depends heavily on the specific problem.
You mentioned tuning the model settings. Can you elaborate?
You adjust the parameters that tell the model how certain it has to be.
Like if it has to be 90% certain before triggering an alert?
Exactly. Adjusting this threshold is key.
That sounds like a sweet spot.
It is, but often trial and error. It's about understanding the context.
And the metrics piece?
Right, just looking at true positives and true negatives isn't enough. We need a more holistic view. A single metric might miss crucial details.
Like, how do we measure a better metric?
Well, we'd need a metric that combines the rates of both true positives and true negatives, along with false positives and false negatives. It's about a much broader perspective, much like thinking about a dog's full performance, beyond just barks.
So, we need a new metric that combines.
We need a metric that considers the balance and the importance of each type of error. It really is about choosing the best tool for the job.
So, Samuel, we're graphing these true/false positives and negatives. This is crucial, right?
Absolutely. Visualizing these helps us understand model performance.
Okay, so this bark-worthiness axis, what's that really measuring?
That's the model's prediction. Think of it as a numerical output from our AI. It's like our guard dog's reaction.
And the other axis?
That's hidden factors. Things the model can't see, like, the repair guy versus the robber.
So, these different events get plotted based on the model's prediction and these hidden factors?
Exactly. The model tries to separate positive and negative events with this vertical line.
The classification threshold?
Yeah. This line is crucial. It's a cutoff. If the prediction is above, it's one thing, below another.
But, how do we know where to put this line?
Well, that's the challenge. It's hard to get this perfect separation. Our model's output is a single number on that axis.
So, lots of room for error.
Exactly. Think of all the nuanced situations. Different examples of the same event. Like, a sneaky burglar or a noisy bird.
Makes sense. So, a single vertical line is enough to classify this multidimensional data?
Yeah. The model maps all this high-dimensional data to this two-dimensional graph.
And the y-axis? It's just a visual aid showing all the other factors not included in the model?
Precisely. This shows the parts the model is missing.
That's helpful.
Right. The ratios help us create better metrics. The proof is in the proportions.
Great. So, it's about understanding those proportions to evaluate how well the model is performing?
Absolutely. It's all about these ratios, helping us create a comprehensive picture of how the model is handling the task.
So, Roxy, this recall thing, it's all about minimizing false negatives, right?
Yeah, exactly. It's like, you want to make sure you don't miss anything important.
Like, if a robber walks by, you want to bark, even if you're not 100% sure?
Precisely. Better to err on the side of caution. A false positive, while annoying, isn't as damaging as a missed threat.
Okay, so, high recall means near-perfect detection of positive events?
That's the goal, but you pay a price. You might bark at a lot of harmless things. Cats, birds, even squirrels.
So, Roxy's pushing this threshold all the way to the left. What does that mean practically?
It means her criteria for barking is very low. Any little hint of something positive, she's going to bark.
So, in this example, practically everything is triggering a bark?
Almost. She's prioritizing minimizing false negatives, which means she's accepting a lot of false positives as a consequence.
That's fascinating. It's like a security system set super sensitive.
Exactly. And in her context, it's the best approach she understands.
But is that always the best solution?
Not necessarily. It depends entirely on the cost of false positives. In certain scenarios, a system with lower recall, but fewer false positives, could actually be more useful. Imagine a burglar alarm with high recall, but it constantly goes off for harmless things like kids playing in the yard.
So, a trade-off between recall and something else?
Precision. Precision considers the false positives. It's the ratio of true positives to the total number of things you say are positives.
So, a low recall, high precision approach might be better in many cases?
Absolutely. It depends on the specific application and what the actual damages are from each type of error.
Interesting. So, to summarize, high recall is about catching all the positive events, even if it means lots of false alarms. But lower recall might be better for precision in other cases.
Exactly. The sweet spot is always a balance.
So, precision, huh? Sounds like a crucial concept for our AI guard dog.
Absolutely. Precision is all about accuracy. It's how often our dog barks at the right things.
Right? Not barking at squirrels. But how do we measure this?
We look at the ratio of true positives, things it correctly identified as threats, to the total number of things it thought were threats. So, if the dog barked at 10 things and only 2 were actually burglars, that's pretty low precision.
So, a high precision means
Fewer false positives. Preston, our dog, has almost perfect precision.
how does he achieve this?
By raising the threshold for barking. He's really strict about what he barks at. He only barks when he's completely sure.
Okay, so high precision means more true positives?
Well, it means fewer false positives, but it also can mean fewer true positives. He's so focused on accuracy, he misses some real threats.
A trade-off then?
Exactly. Precision and recall, how often it correctly identifies the total possible threats, are often on opposite ends.
Makes sense. So, Preston's approach might miss some burglars?
Precisely. He's a super careful guard dog, but might not be effective. He prioritizes accuracy over how many threats he picks up.
Like a security system that's ultra-sensitive to noise, but misses real intruders?
Yeah, kinda like that. It's a balancing act. You need to find the right threshold for your specific situation.
Interesting. So, you're saying we need both metrics?
Absolutely. Precision and recall are important components of our training data evaluation.
Okay, Samuel, we're diving into precision and recall. Crucial metrics, right?
Absolutely. They tell us how well our model's distinguishing between positive and negative cases.
So, how do these metrics work? Can you explain how they're calculated?
Sure. We use true positives, true negatives, false positives, and false negatives. Think of it like this. A true positive is correctly identifying a nodule.
And a false positive?
Mislabeling a non-nodule as a nodule. A false negative is, conversely, failing to identify a nodule.
So, precision is
the ratio of true positives to the total predicted positives. It tells us, of all the things we predicted as positive, how many were actually positive.
And recall?
Recall is the ratio of true positives to all actual positives. It shows us how well we find all the positive cases.
Interesting. How are these calculated practically? You mentioned true negatives. Are those in the code?
Yes, the code has calculations for those. We use existing variables like neg_correct, which is the same as true neg_count. We just need to add variables for false positives and false negatives.
So, it's using the counts of correctly classified and misclassified samples to calculate these metrics.
Exactly. We subtract correct negatives from total negatives to get false positives, and correct positives from total positives to get false negatives. Then we divide appropriately to get precision and recall.
Makes perfect sense. And importantly, what's the significance if either precision or recall drops to 0 during training?
Oh, that's a signal the model is starting to produce bad results. We need to look at the model's behavior to figure out why and fix it.
A bit like a warning light, right?
Precisely. We'll see these in the output for each training epoch now. This will help us track progress and pinpoint issues early.
Excellent. So, the new log metrics function will actually include these?
Yes, it will now display precision and recall alongside loss and correctness. It's important to have all those metrics available for a holistic picture of training.
Okay, Samuel, we're talking F1 scores now. So, this F1 score, it's combining precision and recall. Why not just average them?
Well, averaging them, Alfred, loses crucial information. Imagine a model with perfect precision but 0 recall. Averaging that gives you a 0.5, which is misleading.
Right, that's the crucial point. So, the F1 score does a better job of reflecting a balanced score?
Exactly. It's a harmonic mean, which punishes extreme values in precision or recall. The formula, It seems complicated, but it's really about finding that sweet spot where precision and recall aren't too far apart.
So, what are the trade-offs, practically speaking? How do you see this F1 score used?
You know, in a spam filter, for instance. You might want high recall, catching all spam, but potentially having a high false positive rate, which means low precision. F1 helps find a good balance.
Interesting. And what about the alternative metrics? Like minimum of precision and recall? Why isn't that a good idea?
It's not bad, but it doesn't really reward progress. If one score improves a lot, say recall, but precision remains the same, that improvement is lost. F1 score captures nuance better.
You're saying the F1 scores better because it shows the changes more clearly?
Yeah, if recall goes up and precision stays the same, the F1 score will change noticeably, giving you a better idea of what's improving in your model.
So, we're not just looking at numbers. We're looking at how changes in one metric affect the other. Clearer picture.
Exactly. Multiplication, the geometric mean of the two, that isn't quite as effective either as F1, because it's not as sensitive to changes.
Got it. So, you're saying F1 score is the best compromise?
Absolutely. It strikes a balance. It encourages models to be balanced, and that's what we want. Plus, it's used extensively, so you won't be going off the beaten path, using F1 score.
Great. So, we're going to use it in our logging. What's the practical impact of that logging change?
The code updates log metrics to include precision, recall, and F1, and more details about identified positives and negatives. That allows us to track model performance in more detail, over epochs of training, helping us see if we are making progress and where issues might be.
Okay, Samuel, so our new metrics are clearly problematic. What went wrong?
Yeah, it looks like a classic division by zero error. Our F1 score, which combines precision and recall, is calculated by dividing by the sum of these two measures.
So, if precision or recall are zero, that's a problem.
Exactly. And in this case, we're seeing a lot of zero values, both in training and validation sets. The model's simply not classifying any positive samples correctly. This means our positive prediction count is likely zero, leading to zero for both precision and recall.
That makes sense. How is that even possible?
Well, it looks like our model, especially in the initial training batches, is generating random results. It's not learning properly. The model's initial random weight assignment is affecting its ability to learn the pattern of the positive data. Training samples might also be randomly shuffled.
So, the random shuffling is adding to the chaos?
Yep. Random initialization combined with the random shuffling are making the early batches of the training very noisy. The model isn't learning from them. This is a fundamental limitation of stochastic gradient descent.
Okay, but why is it so random in the training phase?
We're collecting training results throughout the epoch, not just at the end. So, we see the model's volatile behavior directly in the data. The model likely doesn't converge properly because of this noise, and then the validation set also shows similar issues. A crucial step is to ensure proper model convergence in each epoch. This is a typical pattern in machine learning.
So, what's the takeaway?
Our new metrics are exposing a flaw in our model's initial performance. While it's not a major failure, the initial data is noisy and needs to be handled appropriately. It also shows the importance of validation sets and how they help to catch issues early on. It's clear our model needs more careful training and validation.
You know, I've experienced something similar during testing, and that's helped identify issues early on and find bugs in the code. So, this is a good thing?
It's definitely a positive thing. We now have a clearer picture of the areas needing improvements. This is a common step in machine learning, and our next step is to evaluate the root causes of this. Our old metric system hid this critical problem, which is why this is a valuable outcome of our metrics change.
Okay, Samuel, so an ideal dataset. What does that look like?
Well, Alfred, an ideal dataset for training a model, especially one dealing with complex classifications like nodules, needs to be easily separable.
Separable? Like visually separable?
Exactly. Imagine a graph where positive and negative examples are clustered distinctly. Think of two clearly defined groups, not a big muddled mess.
So, no overlap between the classes?
Minimized overlap, ideally. A sharp threshold is key. We want the model to confidently distinguish between the two.
And how does that relate to the imbalance problem we're facing?
The huge positive to negative ratio creates this overlap, right? Lots of negative samples. They just drown out the positives.
You're saying the imbalance is the problem?
Exactly. This imbalanced dataset is making it hard to learn the subtleties of the positive case.
So, what's the solution? Just magically make them separable?
Not exactly magic, but making the data more separable. That's why we want to balance the training data. If we can get them to cluster better at the ends of the spectrum, we can get a near vertical classification threshold.
A vertical threshold? How does that work?
That means the decision boundary between positive and negative is crisp. There's less ambiguity. The model can confidently assign samples to one category or the other. That's much better for accurate prediction.
So balancing the dataset is the key? How do we do that?
We'll need to adjust the proportions of positive and negative samples within our training data. This is crucial for producing good results.
Okay, Samuel, so we're talking about balancing training data. Why is this so crucial? So, you're saying it's a bit like asking a student to identify odd numbers when there are only odd numbers on a test?
Exactly. It's not getting a good grasp of the distinction. We need equal representation to make sure it learns to discriminate.
And what's the practical impact of having imbalanced classes?
This directly affects the model's accuracy. It won't generalize well to real-world situations where the classes might not be equally distributed. It misses the critical details in distinguishing features.
So how does this data reshaping actually work? You mentioned using samplers. Could you explain?
Sure. Samplers let us change how the data loader iterates over samples. Essentially, it gives us control over the order of data presented to the model. But sometimes, the dataset isn't even organized in a way that makes it easy to do this.
So we can't always rely on that?
Exactly. Changing how the data is presented isn't always possible without altering the underlying dataset, which can be complex. So it's often easier to modify the dataset directly inside the dataset class.
Interesting. Can you elaborate on this Luna dataset?
This custom dataset class in our code directly modifies samples. It keeps separate lists for positive and negative examples. Then it alternates between them, creating a balanced training set.
So, it's like creating a custom shuffle.
Yes, to guarantee every other sample is balanced positive and negative. We also control the ratio. This one-to-one ratio approach is very common for this kind of problem.
And this balanced dataset becomes crucial in the training process?
Absolutely. This balancing forces the model to learn to discriminate, because the positive samples are no longer drowned out by negative examples during the initial epochs.
Great, so it trains faster and more efficiently now?
Well, we also use fewer samples but are guaranteed to have a good mix of positive and negative cases.
So, what's the takeaway? How can we apply this to other datasets?
This is crucial, Alfred. You have to understand your data and decide if you can reshuffle it or if you have to create the balance set directly in your dataset classes. The important thing is to understand the data and how it can be modified without losing information.
Okay, Samuel, so we've got this training run with balanced data. It's clearly better than the unbalanced one, right?
Yeah, definitely better results overall. Noticeable improvement in accuracy for positive cases.
But the text says this result is deceptive. Why?
Because there are way more negative cases. Even a tiny error rate on the negatives translates to more misclassifications than all the positive cases combined when you have that many more negatives.
So, a low percentage error on negative cases isn't really representative of good performance overall?
Exactly. The imbalance in the dataset is skewing the apparent success. It's like having a huge, overwhelmingly large number of background objects in an image. Your algorithm might classify those correctly most of the time. But if it occasionally misclassifies those background objects as a particular object of interest, then it has significant performance issues.
Right, so a model might seem great at identifying the smaller thing, but still has huge problems overall. What do the results show about that?
The training results show the model is doing significantly better on negatives. Positive cases are improving, but not as drastically. It's a trade-off. The model's learning to filter out a high percentage of false positives. We're gaining efficiency for the human radiologist by getting them only the cases that really need attention.
So, even with this balanced training set, we're still facing a problem with positives. What did you see in the results with more epochs?
The results show that while training accuracy continues to improve, the validation accuracy for positive cases, while still better than random, fluctuates. And there are significant drops in positive detection after some epochs, which is surprising. It shows a trade-off that we need to understand better.
Wow, that's a tricky one. So, what should we do? More epochs, maybe?
Potentially, more epochs might help. But we need to carefully monitor the validation accuracy curve. We need to watch closely to see if we're overfitting or if it's just a natural oscillation for this kind of data, and how it affects the overall utility. It's likely we're over-optimizing for the negative cases.
You mean it's possibly overfitting to negative cases?
Yes, exactly. It might be memorizing the characteristics of the negative cases too well, while not generalizing to positive cases correctly. This can happen with complex datasets with a large imbalance.
So, the initial balanced run was helpful to see this pattern, but not necessarily a full solution. Interesting, the training and validation data show different behaviors. Something's going on here. Okay, Samuel, so we're seeing overfitting. Can you break that down for us?
Sure, Alfred. We're seeing a problem where the model's getting too good at the training data.
Too good? How's that possible?
Imagine a student memorizing every answer in the textbook. They ace the practice quiz, but they fail the real exam because they didn't learn the principles.
So, the model's not learning general concepts?
Precisely. It's focusing on the quirks of the training data, ignoring underlying patterns.
And you're saying this is shown in the graph?
Yes. See how the training loss is plummeting towards zero, while the validation loss is going up. That's a classic sign of overfitting.
So different losses are showing this.
That's the key point. The positive loss is exhibiting this divergence, but the overall picture might look fine. It's all about the balance of the dataset.
The balance? Can you elaborate?
The overall loss is dominated by negative samples, which are far more abundant. The model's much better at predicting negative samples than positive, so it's not showing overfitting there.
So, it's not really overfitting in a global sense, just with positive examples.
Exactly. This highlights the importance of looking at specific metrics. You have to examine the right metrics, or you could be misled.
What about the 70% of positive samples classified correctly?
That's a critical point. The model is still somewhat generalizing, but we need the training and validation sets to show improvement together.
And how do we stop this problem?
We need to adjust the training process to ensure the model focuses on general principles instead of specific examples. We can explore techniques to prevent it, like regularization.
So, Samuel, you mentioned overfitting. Can you give us a concrete example?
Sure, Alfred. Imagine training a dog to identify different breeds.
Okay.
If you only show the dog pictures of golden retrievers, it might learn to recognize only golden retrievers.
Write a very specific example.
But it won't be able to generalize to other breeds. That's overfitting. The models focus too much on the training data, missing the broader picture of dog breeds.
So, the model's focusing on the specifics instead of the general patterns.
Exactly. The models learned the noise in the training data, not the underlying structure. It's like memorizing the answers to a test, not learning the material.
And what causes this overfitting?
Often, it's a training dataset with too little data, or a model that's too complex for the task.
So, a simple task with a highly complex model could cause that?
Yep. Imagine trying to use a super powerful microscope to identify a single grain of sand. It'll find every tiny imperfection, but it won't give you a sense of the overall property of the sand.
So, how do we fix it? More data?
More data is often crucial, or using a simpler model that can generalize well. Regularization is another key technique.
Regularization? Can you elaborate?
Sure. Think of regularization as adding constraints to your model's complexity. You're forcing it to find general patterns instead of memorizing every detail in the training set.
Okay, that makes sense. So, the solution isn't just more data. Sometimes it's about the model simplicity?
Exactly. And remember, a model that underfits can also be a problem. It's all about finding that balance for generalizability.
Makes total sense. So, underfitting is the opposite, right? The model is too simple to pick up the signals?
Precisely. It doesn't capture the key features and relationships in the data. A simple model might not be powerful enough to grasp intricate patterns.
So, we want a balance between a model that's too simple to capture the information and one that is too complex and memorizes everything.
Absolutely. Finding the sweet spot is crucial for achieving good generalization.
So, Samuel, this overfitting, it sounds tricky. Like a model memorizing instead of learning, right?
Exactly. It's like a student cramming for a test instead of understanding the material. The model sees a picture, and instead of recognizing general patterns, it just tries to recall the specifics of that picture.
So, wrinkles plus glasses equals 65-year-old Frank?
Yep. And that's a problem when the model sees a new face. No general rule, just a bunch of specific memories.
And Frank Jr. in glasses triggers Frank? That's disastrous.
Absolutely. The model's completely lost in the specifics, failing to identify the larger patterns. This overfitting is closely tied to the model's complexity.
How does complexity relate?
Think of the model's capacity like its memory. If it has a huge memory, it can hold a lot of very specific details about many training samples.
But there's just not enough data to use that memory.
Exactly. The problem is you need enough data to fill that memory with general patterns, not specific examples. A model with a massive memory, given few data samples, will simply end up remembering the specific cases.
So, too much capacity for the task, right?
It's like having a supercomputer to run a simple task. You have all this power, but no tasks to make it work. That extra capacity then leads to memorizing instead of learning.
What about fewer training samples? What's the impact?
A small sample size only allows the model to see a few examples of various ages. It struggles to identify common patterns, and hence, overfitting to these few examples becomes more likely. It's a recipe for disaster.
So, like having a limited training set.
Limited data forces a model to memorize individual cases, leading to overfitting. You need a larger, diverse dataset reflecting a range of ages and features to make sure the model learns general patterns.
So, data augmentation, right? How does it actually prevent overfitting?
Well, imagine you have limited training data. A model can easily memorize that data, but that's not generalization.
Right, it's just memorizing.
Exactly.
Augmentation créate synthétique variation.
Think of it like adding more examples to your training set.
But how? Like practically?
We apply changes to existing data points. Flipping an image, blurring it, slightly changing colors.
So, a model trained on these augmented data points isn't just memorizing the original images.
Exactly. It's learning the underlying patterns.
But some augmentations are better than others?
Absolutely. A trivial change, like altering pixels randomly, won't help generalization.
Why not?
The model learns to ignore these meaningless changes. It focuses on irrelevant data. It doesn't learn the actual patterns.
So, flipping an image is better?
Yes, because it maintains the core features, the age in the face, for example.
So, it's about maintaining the underlying characteristics of the original sample?
Precisely. We want these synthetic samples to be similar to the originals, but different enough not to be easily memorized.
So, the challenge is finding the right augmentations that keep the data meaningful for training.
Exactly. Finding those insightful modifications is key. It's a crucial balance.
Makes sense. You're saying it's not just about making more data. It's about useful data?
Exactly. We want variety without losing the essential information for the task.
Okay, Samuel, so we're diving into data augmentation for CT scans. This is crucial, right? Why is it so important? Right. So these augmentations, mirroring, shifting, scaling, rotating, adding noise. What's the deal with mirroring, specifically?
Mirroring, flipping images left-right, up-down, or front-to-back, is a simple but powerful technique. It doesn't change the underlying data, just the orientation.
Okay, got it. So, the transformation matrix adjusts the view.
Exactly. We use PyTorch's functions to manipulate the image. The transformations are controlled by the augmentation_dict. The grid_sample function does the actual mapping.
Shifting, scaling, what about those? Those sound a bit more complicated.
Shifting moves the nodule within the image by a random offset. It's about making the model more resilient to the exact location of the nodule. Remember, real-world images aren't always perfect. Also, scaling up or down mimics different potential variations in the images. It also helps the model generalize better.
So, the scaling and shifting blur things a little bit, right?
Yes, a bit. Introducing trilinear interpolation. It means that values between the actual voxel values are interpolated, which can give a slightly blurred or smeared appearance around the edges. It's a bit of a trade-off, to be sure. It makes the model better at seeing that the nodule isn't necessarily perfectly centered in the image, or that it might be slightly different in size.
Rotation, now that's interesting. You said we're only rotating in 2 dimensions. Why?
Because CT scans, unlike some other images, have voxel sizes that aren't uniform along all axes. Rotating in 3 dimensions could introduce a significant loss of data fidelity, blurring in the non-uniform dimension, and wouldn't accurately reflect the actual variation in the data. We're keeping the index axis special, the axial dimension, because the voxels aren't cubic.
So, rotation's only in the XY plane, you're saying? How about noise?
Noise is a bit more aggressive. Adding noise is essentially making the classification task harder on purpose. We only add it to the edge of the image.
So, the model is learning to find the patterns in the data despite the noise, imperfections?
Exactly. By introducing these varied augmentations, we're creating a more comprehensive dataset. This means the model will perform better on unseen real-world data, which is the whole point of augmentation, right?
Absolutely. So, it's like giving the model a harder test in training, right? The augmented dataset is a bigger and more robust dataset.
Exactly. And importantly, the data augmentation is done before storing it in a cache, so the augmentation is applied each time, introducing a level of
Okay, Samuel, we've seen how data augmentation improve things. So, tell us about this training process.
Yeah, we're training models, one for each augmentation type, plus a final model combining all. Then, we'll look at the results in TensorBoard.
How are we making sure to turn augmentations on and off?
We're adding command line arguments. Think of it like flipping switches, enabling or disabling different effects.
And how do these arguments affect the augmentation dictionary?
The Python code looks at these flags, adding augmentations to the dictionary. It's crucial for flexibility.
You mentioned a dictionary. Can you elaborate on that?
It's like a key value store, right? Flip maps to a Boolean, offset to a value, etc. It's a great way to keep track of augmentation choices.
So, practically, what does this code do?
It basically sets up which transformations to use during training. The script checks flags to decide on parameters.
So, what are these commands we're running? They seem a little cryptic.
Those commands run the actual training process on different configurations. Each one uses a distinct combination of augmentations.
Why so many variations?
It's vital for comparing results. We want to see which augmentations work best.
The commands also vary epochs. What's important about epoch numbers?
Epochs represent full passes through the data, and more epochs usually mean more training time. We need to strike a balance.
What's the deal with the balance flag?
Balanced aims to train models that aren't overly influenced by any one class. That's a good idea.
So, we're launching all these jobs at once?
Yes, we run all these models in parallel, which is perfect for GPUs. They should work fast.
This all sounds time-consuming. How long will this take?
Depending on your hardware, training could take a while. It's worth considering reducing epochs or specific augmentations, if needed.
Why are we looking at TensorBoard?
To visually track training progress. You can see things like loss, accuracy, and other metrics over time.
So, TensorBoard allows us to see the performance of all models at once.
Exactly. We look at graphs to determine optimal settings.
What's the crucial takeaway from Figure 12.22?
The combined augmentation works better overall than individual ones. The fully augmented model has superior recall for positive cases. Noise augmentation, though, is counterproductive.
That's interesting. Why the poor performance with noise augmentation?
Noise makes the task harder. The model might get distracted and struggle to extract essential features.
Rotation augmentation seems strong.
Rotation augmentation often has great precision and recall, improving F1 scores.
So, we're sticking with the fully augmented model.
Yes, given the priority on high recall, that's the best choice. However, other combinations might perform better with different needs.
Excellent. Thanks, Samuel. So, we've refined our model evaluation. Good work. But what about data scarcity?
Yeah, a critical point. Sometimes, you have tons of data. Other times, not so much.
Exactly. How do we handle that?
Well, synthesizing data is powerful. Making representative training samples from limited data helps a lot.
Makes sense. This synthesizing idea sounds interesting. Can you give an example?
Absolutely. Imagine you're training a model to identify cats in images. Limited data means fewer cat images. You could synthetically create variations. Change the lighting, add different backgrounds, even slightly alter the cat's features.
So you're artificially expanding the dataset?
Exactly. It's like having a small garden. You need more flowers. So we build special tools to multiply what you have.
Interesting. What are the downsides to this synthetic approach?
Well, there's always the risk of creating data that's not really representative. You could introduce biases or inaccuracies. So quality control is key.
So, you need good quality control measures. That makes sense. Now, about moving on to finding nodules automatically?
Right. We've got a working classifier. Now we need to automate finding the areas in medical images that might contain nodules.
So, we're moving from classification to nodule detection?
Precisely. Chapter 13 will focus on this. Then, Chapter 14, we'll use our trained nodule detecting system to give our classifier even more data. And then train one more classifier to distinguish between malignant and benign nodules.
That's a clever two-step process. So the classifiers are building upon each other.
Exactly. More sophisticated classifiers building on the foundation of simpler ones. It's like building a robust medical imaging system.
Very cool. So,
Yep. It's efficient. It's a neat iterative process.
sounds like a good plan. Any potential issues with building more classifiers to evaluate each step of detection?
There's always the risk of cascading errors. If the nodule detection system is flawed, it'll introduce inaccuracies into the second classifier. Very important to test every step thoroughly.
Good point. Thorough testing at each stage will be crucial. We must take care to catch these issues early.
Precisely. Rigorous testing is crucial for accurate results.